Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Hello. Okay. Good morning, everyone who are in this room and or possibly watching online. So I would say, well, welcome everyone back to the university, right? Okay. So today is the first talk of the Tah Poe seminar series 58, right? So today's speaker is Dr. Pongwit Srisangyingcharoen. He's going to give us about on-shell recursion relation for string scattering amplitudes at 3 levels. So please welcome. Yeah.
Okay. Thank you for the nice introduction. And today I will talk about, as it said in the topic on show on the slide here, on-shell recursion relation for string scattering amplitude at 3 levels. So basically, what I'm going to do is I'm going to apply the concept of on-shell recursion relation to the string scattering amplitude, where the on-shell recursion relation is the useful relation in quantum field theory. But now I'm going to apply it in string scattering amplitude. The talk is based on my recent paper, one already published and one is about to publish soon, hopefully. Okay, and here is the outline of this talk. So first of all, we need to know what is the string scattering amplitude, and then what are the on-shell recursion relation, and then I'm going to apply the concept or the technique of the on-shell recursion relation to the string scattering amplitude. So which is divided into two parts, which is the on-shell recursion relation for the open string amplitude and the on-shell recursion relation for the closed string amplitude. But for this time being, I'm going to focus on just only 4 points, because for the end point, it would be more technical to discuss, and due to the time limited of this talk, I will just focus only for 4 points for in the case of closed string amplitude, and then I'm going to summarize it. So first of all, let's talk about the string scattering amplitude. First, what about this? What is the string theory first? So you may have known that the basic concept of the string theory is that the most fundamental object is not the point particle, but instead it is the string, and the vibration of the string can be interpreted as fundamental particles such as gauge boson, maybe photon, gluon, graviton, and etc. etc. And if you consider the superstring theory, it would the state would include the fermion as well. And to describe the string, we need to know the dynamic of the string can be obtained by the action or the Lagrangian. Okay, and here is the action on the slide. Here is the action of the string theory. Okay, so for the string, it is the 1D object, right? When time go on, the string sweep out the space time to generate what is called the worldsheet. Okay, on the left hand side here, it is the open string. The open string, when it sweep out the space time, we get the 2D worldsheets as a plane here. It's like a paper sheet here, and for the code string, when it sweep out the space time, it generates like a tube worldsheet, okay, which can be considered as a cylinder here. And the dynamic of the string theory can be described by this field X here. You can it's called the space-time field X here. In 4D, you can imagine it. You can imagine it like a 4 vector, the four space-time vector. But in case of string, it just you keep arbitrary dimension, like let's say the dimension D. This we call it like the D vector here, where the Bosonic string D is equal to 26, or in superstring theory, D is equal to 10. And the field, space-time field here depends on the point on the worldsheet here. And here, the tau and sigma here is the point of the worldsheet here. The dynamic of the string can be described by here these two actions. The first one is the Naresuan action here, which is the generalization version of the relativistic point particle. You may familiar with the relativistic action for the relativistic action, point particle action, where this would be like the x dot square. But now, if we generalize it, we have another derivative, which is the spatial derivative in with respect to the worldsheet coordinate. Okay, but the form of the Naresuan action is hard to deal. It's quite hard to deal if we would like to quantize it because of the square root, the nature of the square root of it. It's quite hard to deal. So we need an equivalent, classically equivalent action, which is called the Polyakov action. Here, so the Polyakov action written below here, you can see it is in the form of the quadratic form, which is much easier to deal with. And you can see the form, if you recall it is equivalent to the Klein-Gordon Lagrangian, which is easier to deal with. Okay, where the G here is it is called the worldsheet metric. It is the metric of the worldsheet nothing to do with the space-time metric. Okay, then let's talk about the string scattering. So as I said earlier, the most fundamental thing of the string theory are strings, right? So instead of the scatter of the point particle, we replace it by the string. It is the scatter of string. So in this slide here, it shows the scatter of 4 strings. So maybe you can think of it as, or as the process where there are two strings coming in and two strings coming out, two strings going out here. And the scattering can be described by the field on the worksheet. Okay, the field on the worksheet here. On the first case, it is the closed string scattering, and on the second case, it is the open string scattering. And one of the property of the string theory is that you can freely deform, not freely deform, you can deform the worksheet in a certain way such that the worksheet need to preserve some property, which is like you need to preserve the angle of the vector on such space. On such space, it's called conformal map. You can conformal map the worksheet into the form that we more familiar with. For example, you can deform the worksheet here into the sphere, and the string state here. There are 4 string states here. It is encoded in the as a puncture on the sphere. Okay, and then by this you can do another mapping, which is called the stereographic projection, to map the 2D sphere into the complex plane, where the puncture on the sphere, on the surface of the sphere, will be mapped into, let's say, the point on the complex plane. Okay, so now the object here where the 4 string scattering can be mapped totally into some object into the complex plane. So the language that describes the string scattering amplitude is nothing but the complex function on the complex plane, where the state of the string is encoded into certain point in the complex plane. And that point, in this case, we say that we turn the state into what is called the vertex operator that acting on this point in the space, in the 2D space. Okay. Similarly, in the case of open string, we can conformally map this shape here into a disk. Along the boundary of the disk, the states are encoded or inserted along the boundary here. Similarly to the closed string, the disk can be stereographic projection into the upper half plane. Not the full complex plane, but we need an upper half plane because we need to have the boundary, because the open string have boundary. So we need, when we do a mapping, we need a boundary of the 2D space as well, where now these states are inserted along the boundary here, which is on the real axis. Okay. And what are the form of this state? So, as I said earlier, we encode all the information of the state as the vertex operator, acting on each point on the 2D space, on the 2D plane, right? Here, the general form of the vertex operator are given in equation 2 here, where the left-hand side here is the open string vertex operator, and the right-hand side here is the closed string vertex operator. Okay, you can see that in the open string vertex operator, it is a line integral. It is a line integral because, as I shown earlier, that the state of the open string must be located on the real axis, right? It needs to be inserted along the boundary of the worksheet. So that's why we need, you need to insert the vertex operator along the real axis or along the boundary here. And then for the code string, there is no such restriction. You can insert the state in arbitrary point on the 2D plane. Okay, but due to the conformal invariant, we need to do we need to integrate all the possible points of the complex plane, dz square, d square z. And then we have state encoded in the vertex operator. So now we can give an expression for the string scattering amplitude as given in the equation 1, which is basically the expectation value of the product of all of the vertex operator. Okay, you see that all of the string state here are encoded in this vertex operator here. So, and then you can compute things with equation 1 here. I'm not showing you how to compute it, but finally, if you compute it using maybe using the path integral formalism, you can get the general expression for the string scattering amplitude as equation 3 and equation 4, where the equation 3 is the code string scattering amplitude here. You can see that it's the integral is the 2D integral. Here it is a surface integral of each vertex point. And where the equation 4 here is the open string scattering amplitude, where the state here is inserted along the boundary here. And there is a special, and there are special thing on the open string scattering amplitude because the states are inserted along the boundary. We can have the concept of ordering of such state, right? Let's move it backward here. You have the state here inserted along the boundary here, right? So you can say that the first point, I would insert the state 1. At the second point, I insert the state 2 and 3 and 4 and so on. You have the notation or notion of ordering in such the way that here I insert the state 1, and the position of the state 1 must be lesser than the state 2, and at the state 2 must be lesser than the state 3. So you have the notion of ordering in the open string scattering amplitude here. That's why I rewrite it here as 1, 2, 3, and n here. There is the notation or notion of ordering in open string scattering amplitude here. And this line integral need to be the integration region need to be aligned with this order as well. Okay. Okay, x is just real variable, but z here is a complex variable. You see that we integrate over all the complex plane in the code string, and we integrate over the real variable in the open string. Okay, we will here for the form of equation 3 and equation 4, it is the starting point of our talk here. I will use this form to generate our result on on-chain recursion relation. Okay. Okay. Next, let's talk about the on-chain recursion relation. What are the on-chain recursion relation? In quantum field theory, the on-chain recursion relation is a useful concept. Okay. it is the relation that you can write the higher point amplitude in terms of the product of the smaller point or the fewer point amplitude. It means that you can start with, it means that for any higher arbitrary point, let's say maybe 10 point amplitude, you can construct it with much more smaller point product with much more smaller point. Maybe you start from the product with 3 point and 4 point and etc. The basic idea can be captured by this picture here. On the left hand side, you have the higher point amplitude, let's say the end point amplitude here, and then you factor it into two parts. Let's say the left hand side amplitude and the right hand side amplitude here. By separating in this way, you have the smaller point amplitude here on the left hand side and another smaller point amplitude in the right hand side here. And this relation called on-shell recursion because these two amplitudes are on-shell, meaning that all the momentum here of the left-hand side amplitude and the right-hand side amplitude are on-shell, meaning that it satisfies the match shell condition. Okay, and here is the expression for the general it is a general expression for the on-shell recursion relation here that the endpoint amplitude or the higher point can be written as the product of two smaller amplitude product together, divided by the propagator of, let's say, intermediate particles, and the intermediate particle contain momentum p here. So here I write it as sum over all possible channels. By sum over of all possible channels, I mean the channel sum over possible channel possible. I mean that the intermediate, all of the possible intermediate momentum possible. For example, the first channel would be like the capital P would be K1 plus K2. Another channel would be K1 plus K2 plus KT. Another channel would be K1 plus K2 plus KT plus K4 and etc. etc. Okay, so let's see how can we gain this relation. In order to obtain this relation, we use the concept of complex analysis to do it. So first, what we are going to do is we are going to deform the momentum of the scattering amplitude or of the particle here. We will deform, let's say, two momentum. This is arbitrary. This choice is arbitrary, but I will use K1 and Kn to deform. Okay. The momentum K1 are deformed into K1 hat equal to K1 minus ZQ, and Kn are deformed to be Kn hat, which is equal to Kn plus ZQ here. You can see that now we deform the real momentum into the complex momentum. See, Z here is the complex variable. By deforming this way, that means we turn the amplitude into the complex amplitude, because now the amplitude depends on the variable Z, complex variable Z. But by deforming in this way, we require that the new shifted momentum need to be on shell, meaning that k1 square need to be equal to k1 hat square, and kn square need to be kn hat square. Okay, and if that means q dot q equal to q dot k1 equal to q dot kn need to be 0. Okay, and the new version of the momentum satisfy the momentum conservation, which is obviously because of minus zq will cancel out with plus zq. The momentum is conserved, and it is on shell because of this condition. To obtain the original amplitude here, to obtain the original amplitude, you just set z equal to 0, right? If you set z equal to 0, that means you haven't shipped anything, right? If you set z to equal to 0, that means you obtain the original amplitude, right? Simply as that. But there is another way to make z equal to 0 by using the Cauchy theorem, right? And by the Cauchy theorem, you can have the z equal to 0 equal to here sum over all possible residue of this guy here, a z over z here, right? Here, sum over all possible pole in the complex plane. When z not equal 0. Okay. And if you compute this guy, what you have is this on-shell recursion relation here. As I said, it factorized amplitude into two parts. The left-hand side amplitude, the smaller one, two smaller amplitude product together divided by the propagator of the intermediate particles, which are the scattering channels of the amplitude. And this is how you gain this is how you obtain the on-shell recursion relation in quantum field theory. But for the quantum field theory, it is relatively easy than the string theory, because you know that we need to obtain this relation by consider the residue of the amplitude, right? But you know that for the quantum field theory, the residue, by consider the residue, that means you need to sum of all possible pole, right? But the quantum field theory have easy pole structure than the string theory. For example, you may have like the pole as 1 over propagator p square plus m square. It is, and that pole is basically the simple pole, right? But there are no such, there are no such things in the string scattering amplitude. That is the main challenge of applying this technique to the string amplitude. Okay, and for this expression, you can see that you need to sum over all the physical state of the intermediate propagator. That means, but in the string state here, there are infinite tower of string state here. So that is another main challenge. And here I remark here that there is no general expression that describe the costring scattering amplitude for the on-shell recursion. I mean, there is no on-shell recursion relation of costring scattering amplitude have been expressed before. So that's why I work in this project. Okay, let's do how to apply the on-shell recursion relation to the open string scattering amplitude first. So the goal is to compute equation 5 here. The amplitude needs to be equal to sum over all the pole of the residue of the amplitude here, the deformed amplitude AZ by Z here. And for the open string, here, the expression is in equation 6 here, right? You may notice here that we already deform the momentum K into K hat. Here, we already deformed the momentum K into K hat, where the K hat here is just shifted momenta here, where K1 shifted into K1 hat and Kn are shifted into Kn hat here. And another remaining momentum are unchanged. K2, Kt to Kn-1 are unchanged here. But you can see that the main challenge here is that there is no explicit pole structure of the open string scattering amplitude form here. We expect to have something like this, which is the pole structure here, because we would like to compute the residue, but we know that the formula for the residue, right? We can compute the residue easily if we could have the pole of the polynomial form, for example, simple pole or higher order pole. But it is not obvious in the equation 6 here how we would get this kind of pole from equation 6. Okay? What I'm going to do is I'm going to transform the equation 6 here into another form, which is I'm not going to drive you into much detail, but believe me that all of the color order open string amplitude can be written in the equation 7 here, where the function b here is expressed in the equation 8 here. Now we change the integral into what is called the Gaussian hypergeometric function equation 8 here, where now the integral region is inside 0 and 1. It's all inside 0 and 1 here. Okay, where the parameter here are expressed in equation 9. Okay, I'm not going to give you much detail about it. But what is important here is the Sij and S1 to the I here encode the kinematic variable here, encode the momentum here. Sij equal to alpha prime ki plus kj square, and S1 to the I equal to alpha prime k1 plus k2 plus kt plus up to ki square here. Okay. So that means when we shift the momentum here, k1 into k1 hat and kn into kn hat, we have the complex variable set in the exponent of its integrating variable wj here. We can see that because we shift the momentum here, the complex variable set is at the exponent of it wj here. That means it is possible that the pole would be hide in this piece here, in this integrand here. Okay, and j here run from 1 to n minus 3. That means we have n minus 3 poles possible, which is makes sense. Okay, so as I said earlier, the pole could be from this integral, and there are 3 minus 1 pole. But for simplicity, let's talk about the first pole, Z1. Let's talk about the first pole, Z1, which is here. It could be from this term, W1 here, where the Z1 is, again, as the exponent. And there are W1 hiding somewhere here in this product as well. The point is, we could regain the form of the pole if we could integrate out this integration of the variable W1. Okay, I'm going to integrate out the W1. Okay. What I'm going to do here is, you know that here the product here obviously is contain W1, right? It is the product of W1 to WL here. It contains W1. So what I'm going to do is I'm going to use the binomial expansion to this term 1 minus the product of WK here, using the equation 12 here. So in this binomial expansion, it allow us to factor out the W1 here. So now we can by using the binomial expansion, I factor out the W1. Then I product the W1 together here to get this form, and then I can easily integrate out this form, right? It is the basic integration, right? Integrate of the polynomial is give you this from the last box here. It give you the simple pole of the Z1. Here you can see that Z1 is when Z1 equal to, let's say, S12 plus N1 plus M plus 1, it is a simple pole. And by the simple pole, you can evaluate the residue easily. Okay. Okay. Here I really label sum over all parameter AI here as the new parameter M here. And the pole occur at here at S12 plus N1 plus M plus 1 divided by some factor. This is nothing because here this factor comes from the fact that we rename the Z1 before, but it does not matter much. So if we consider the residue of the function Bn over Z here, it gives you this expression here. And 1 over S12 plus N1 plus M plus 1 here is basically the scattering channel, the propagator of the scattering channel. Okay. But as I said, this is just the residue of the first pole, Z1. We can compute the residue of the remaining pole using the same procedure. Okay, using the same procedure to get the equation 17. Here. Using the equation 17, to get the equation 17 here. Where now the propagator here is here in this denominator here. Okay, let's see if it makes sense. Let's see if it makes sense. So in case of the tachyon scattering, all of the Ni here is equal to -2. And you can show that the denominator turn into something like equation 18, which is mean that the first term here, K1 plus K2 plus K3 up to Ki plus 1 here is nothing but the intermediate momentum. That means the intermediate momentum square, I mean the pole is the intermediate momentum square plus m minus 1 over alpha prime. Here, where m run from 0 to infinity, that means it means that our propagator have the full spectrum of open string, because when m is equal to 0, you have the negative mass, which is the tachyon, tachyonic mass minus 1 over alpha prime. If m equal to 1, it is massless because the mass square equal to 0. Okay, and if m equal to integer more than 1, you get the massive state of the string spectrum. So, as you can see, we can regain here the equation 17 here tell you that we can regain the on-shell recursion relation for the open string scattering amplitude here. Okay, but as I said, the challenge is that you need to deal with the pole structure of the string scattering amplitude, which is not clear to have the simple pole. But if you manipulate in the way that I already given, the simple pole will be appear, and then you can compute the on-shell recursion relation from that simple pole using the residue theorem. Next, let's talk about the on-shell recursion relation for the core string amplitude. But for the to keep it simple, I just consider only for the 4 point here, because I mean for the general endpoint, it would be too technical. And if you would like to know more, you can read my paper. Okay. Okay, let's repeat the calculation again, but for the core string amplitude. Yeah. Again, the goal is to compute the equations 19 here. The core string 4-point core string amplitude must be equal to sum over all possible pole of the residue of these deformed amplitude over Z. Okay, where the 4-point core string amplitude is defined in equation 20 here, where we deform the momentum P1 into P1 hat and P4 into P4 hat, as P1 turn into P1 hat equal to P1 minus ZQ. sorry, and P4 into P4 hat equal P4 plus ZQ. Okay. Okay. There are more challenges for the coarse-grained scattering amplitude in order to formulate the on-tail recursion relation. First of all, there is no exhibit pole structure of this form because we would like to find the residue, right? We expect the pole like this because it's easy to deal with. But it's not clear from the equation 21 how could we get this such pole. I mean, do not confuse with Z and Z tilde here. In this case, Z here, it is the point in the complex plane. But the Z tilde here, Z tilde is another complex variable where we deform the momentum P here. It is a quite bad use of variable, but we deform the P1, which is the real momentum into the complex momentum depend on Z tilde. Z tilde is another complex variable apart from the complex variable of the vertex operator set. Okay, so we expect the first challenge is how can we get the pole structure of this polynomial form here. The second challenge is that we know that from the open string that I showed you earlier, the pole structure of in the case of open string, it is the simple pole, right? It came from this kind of integral in the open string, but there is no something like this. There is nothing like this term in the closed string. Why? Because the open string we deal with the real integral, right? And we deal with the real integral, and the real integral need to be I mean the line integral need to be in this region 0 to 1, but there is no such this integral appear in our expression for the coarse string. And another challenge is that the expression here 21 is lack of symmetry under the permutation of the momentum pi. So in closed string, you expect that for the 4 points, you expect that you would have the pole, all of the pole possible, meaning that you need to have the S channel, T channel, and U channel, right? S channel is like K1 plus K2, T and U. To be honest, I made out one is 1 and 3, and another one is 2 and 3. So we expect to have this kind of symmetry, but looking at this 21 equation here, when we shift the momentum P1, the complex pole would be generated from this exponent here. And that means that we could have the pole from the, let's say here, it is the S channel because it's involved momentum P1 and P2. So that means that this expression is not manifestly exhibit the symmetry between the permutation of the momentum. So what would we do? Let's talk about how we can regain the pole structure of the polynomial form first, because we need to find the residue, right? So what I do, or what we do, I mean, uh, what we do here is we rewrite this term here, the polynomial term here using the Schwinger parameterization here, equation 24, and then we can rewrite the shifted amplitude into the equation 25. Now here, the beta here the beta here encodes the kinematic variable and the set tilde here, which is a complex variable here. So the pole would be inside this integral t, right? Because the beta is the exponent of the t here. But writing this into the Schwinger parameterization, we can see that this expression of the integration of the set variable is nothing but the Gaussian integral, right? You can see that we have the exponential of absolute set square here. It is basically the Gaussian integral here. So that means we can use the technique of Gaussian integral in order to evaluate it. So by doing it, we using the binomial expansion again of this term here of the equation 27 to turn the amplitude into equation 28 here. You can see here now, the right hand side here is again is nothing but the complex Gaussian integral. dz square, integration of dz square of exponential of minus absolute z square t times with z to the power of a and z bar to the power of b. But we can evaluate it using the complex Gaussian integral by turning the polynomial of z a and z bar to the power of b to the functional derivative of the Gaussian integral with the source term j and j bar here. And then when you do the derivative, you evaluate when the z equal to z, you evaluate in the case of j equal to j bar equal to 0 here. And you can see that this requires that a need to be equal to a. The exponent a need to be the exponent b unless this equation 29 would be 0. Okay. So after the integration, after the complex Gaussian integration, we would obtain the equation 30. Okay. So what it left here is just the polynomial integral of the polynomial here of the variable t here from 0 to infinity. By such, we can rewrite the variable t into we can change the coordinate into the exponential one. Let's say t equal to e to the w here, which give you the Dirac delta function. It gives you the Dirac delta function here. Inside the Dirac delta function, it is the beta plus b. But remember that the beta is the complex variable, right? The beta contain, let me go back again. Here, the beta defined in equation 26 here is contain the complex variable z tilde here. And the kinematic variable of P1 plus P2 square here. Now the beta is inside the is inside the Dirac delta function, which is we need to deal the problem. This caused another problem, of course, because now the pole is inside the delta function. How can we tackle this problem? It turned out that you can expand the Dirac delta function into the Lorentz series, which is called the formal distribution of the Dirac delta function defined in equation 33 here. Now, that means we can rewrite the Dirac delta function as sum over of the higher order pole, all of the pole possible here. You can see that this pole here to the power of minus n, where n is some integer here. I mean, if n is negative, there is no pole, right? But if n is positive, there is a pole. There is simple pole, and there are higher order pole when n is greater than 1. Okay. And because we rewrite it as the higher order pole, we can use the residue theorem of the higher order pole here written in equation 35. And by using the residue theorem, we can show that the residue of the function times with the Dirac delta function is nothing but that function evaluated at the point set 0 here. But the point set 0 is just mean the point of 0 delta function. I mean, set equal to set 0 is give you non-zero value of delta function. And by using that relation, you turn the residue, this residue of the amplitude into the propagator here, into the propagator as nicely as that. You can see that A run from 0 to infinity. And this term here is the mass square of the string state here. Meaning that when this mass square cover all of the possible mass spectrum of the intermediate coarse string amplitude from the tachyon to massless to the massive state here. And you can see that this is just only one channel. It is basically S channel because it contains only P1 plus P2 square. It contains only one channel, but we expect that the coarse string is unlike the open string. Because for the open string, we have just one channel. But for the coarse string, there is no restriction. We could have all possible channels. What could we do here is just we could naively take all of the possible permutation of the external momentum in this form here. Just put it by hand here. This is just put it by hand because we know that if we give only the equation 37 here, it would lack of the symmetry or permutation of the external momentum. So in order to recover such symmetry, we put it by hand by sum over all possible permutation of external momentum by hand. So then we could regain the 4-point, the on-chain recursion relation for the 4-point coarse string amplitude. And again, for the endpoint generalization, you can discuss this archive code here if you would like to know more. Okay, let's summarize. So the key idea of the on-chain recursion relation is that you use the analytic continuation of the of the momentum into, you deform it into the complex momentum, and you use the Cauchy theorem or the residue theorem to rewrite the amplitude as the sum over all possible pole of the residue of the deformed amplitude over set here. So in this work, I developed this technique, but I use this technique in order to evaluate, is it possible to have the formulation of this on-chain recursion relation but for the string theory? And the answer is yes. But it's not as simple as in the case of quantum field theory, because the pole structure of the string scattering amplitude are hidden. So we need to somehow try to crack the pole structure of the string scattering amplitude, as I given in this talk. Okay. So okay, in my work, we have developed a systematic computation of the on-chain recursion relation for both open and closed string amplitudes here, and the propagator. It turned out that the propagator, the on-chain propagator, cover all possible closed and open string state possible, which is a good sign. That means we are on the right track here. And okay, and more information we can discuss these two archives here. And thank you.
Any questions? Anything from online? No. So, well, let me ask you like a very naive question. So, you just mentioned actually what you dealing with now is that you try to construct string scattering amplitude, right?
The on-chain recursion version of the string scattering amplitude.
Okay, and and you have to deal a lot with the pole issue, that kind of stuff.
Yes, yes.
Right. So my question is that, so in quantum field theory, do we have this kind of the same problem?
As I said, that in quantum field theory, there are nice. It is nicer than the string theory because it have only simple pole.
Okay.
It has only simple pole, which is manifestly exhibit in the form of quantum field theory amplitude, because we have something like something like this, and here you have something like the pole.
Yep. Mm-hmm. That's we commonly
P1,
have.
P2, something like this.
Mm-hmm.
And then the again, how to obtain the on-chain recursion relation, we deform P into, say, like P1 hat equal to P1 minus ZQ here. So that means we analytically continue the real variable into the complex variable, such that this, because this need to be on-chain as well, it need to be conserved momentum here. This would be somehow deformed into like this. Okay. Like this. So the pole would be from this. When the pole would be from where this vanish when z equal to some to the pole, to the value that where this pole exists. But you can see that it is explicitly stated here that there are pole which is in the form of the polynomial pole here, but there is no such thing I mean, there are such thing in the string scattering amplitude, but we need to crack it to see such a pole.
Okay, I see. So what you mean is that so in the standard quantum field theory is the pole behave nicer, right?
Yes.
But in this
nicer.
situation, it's kind of more complicated
Yeah,
or
and more tricky to,
yeah,
to,
it's,
to
yeah,
deal
I
with
see.
because you see that they especially need to deal with the residue.
Yeah,
So
yeah,
that
I
means
see.
you expect to have like the simple pole of all the high to the pole that you have. I mean, it's easier to deal with
I see.
such pole.
It's not kind of like very trivial things to see right directly somehow.
Yeah.
I believe.
And as is shown you earlier, for the case of pole string, we have like the delta function pole,
Mm-hmm.
which is which is not trivial,
Mm-hmm. Mm-hmm.
right? But we can make it trivial by using
Okay.
the expansion into the higher the pole.
I see. Okay. But still complicated anyway. All right. Okay. Any question? Any more questions? You'd like? Okay.
why three levels ครับทำไมถึงทำในที่ T level ครับ
Because it's easier. You can see that even it is the simplest case, the math is also very complicated.
Why 3 level?
It is possible to consider it maybe in one loop or higher the other loop, but
Yeah.
it would be in the future. And maybe I'm not sure it would be in near future.
But I believe in principle we can move beyond
Yeah,
three level, of
Yeah,
course.
yeah.
But even the 3 level, the maths is already complicated. I believe. Right?
Yeah. But the answer or the final answer is it shows the nice behavior as it shows that it recover all the possible spin state of intermediate spin state possible, which is a good sign that we are on the right track.
Right. Good. Because so normally what we did is we just start from the simplest case first, right? To see what really happened. And then if we get something nice and then something concrete, and we can move beyond. Normally that's what we do, I believe. Any more questions or anything? Okay. I think is okay. If not, then let's thank Ajahn Pongwit again for a very nice talk.
Thank you.
And so before we start today, I would like to ask you guys to to finish the survey form. So for the people online, you can do the survey form through the QR code, right? And then you can give us a comment on the feedback, and then we can use that to improve our activity next time. And then so stay tuned for the next Tah Poe seminar. Okay. Thank you very much. Bye bye for today. Bye.